Hello, today our topic is supervised learning. As discussed earlier, supervised learning is a mapping from the input to an output whose correct values are provided by a supervisor. Learning a class from example. Let us say we want to learn the class C of a family car. We have a set of example of cars and we have a group of people that we survey to whom we show these cars. The people look at the cars and label them. The cars that they believe are family cars are positive examples and the other cars are negative examples. Class learning is finding a description that is shared by all positive examples and none of the negative examples. Doing this, we can make a prediction given a car that we have not seen before. By checking with the description learned, we will be able to say whether it's a family car or not. Or we can do knowledge extraction. This study may be sponsored by a car company and the aim may be to understand what people expect from a family car. Now the features that separate a family car from the other cars are the price and the engine power. These two attributes are the inputs to the class recognizers. Note that when we decide on this particular input representation, we are ignoring various other attributes as irrelevant. Though one may think of other attributes such as seating capacity and color that might be important for distinguishing among car types, we will consider only price and engine power to keep this example simple. The training set for the class of a family car. Each data point corresponds to one example car and the coordinates of the point indicates the price and the engine power of the car. The positive sign denotes the positive example of the class, that is a family car, and the negative denotes a negative example, that is not a family car. It's another type of a car. Now let us denote the price as the first input attribute x1, example in US dollars, and the engine power as the second attribute x2, whereas the engine volume is in cubic centimeters. Thus, we represent each car using the two numeric values where x equals to x1 and x2. And its label denotes its type where R equals to 1 if x is a positive example and R equals to 0 if x is a negative example. Now each car is represented by such an ordered pair of x, r and the training set contains n. Such example is given by x equals to xt, rt to the limit of nt where t equals to 1 and the t indexes different examples in the set. It does not represent time or any such order. Our training data can now be plotted in the two-dimensional x1 and x2 space where each instance of t is a data point at the coordinates of x1 to the power t, x2 to the power t, and its type, namely positive versus negative, is given by our to the power t. Example of a hypothesis class. See, the class of a family car is a rectangle in the price engine power space. This is the rectangle space. After further discussions with the expert and the analysis of the data, we may have the reasons to believe that for a car to be a family car, its price and engine power should be in a certain range. That is, P1 should be less than equals to price less than equals to P2, and E1 should be less than equals to engine power should be less than equals to E2 for all the suitable values of P1, P2, E1 and E2. Equation thus assumes C to be a rectangle in the price engine power space. Equation fixes H, the hypothesis class from which we believe C is drawn, namely the set of the rectangles. The learning algorithm then finds the particular H belongs to the capital H to approximate C as closely as possible. Though the expert defines the hypothesis class, the values of the parameters are not known. That is, though we choose H, we do not know which particular H belongs to caps H is equal or closest to C. But once we restrict our attention to this hypothesis class, learning the class reduces to the easier problem of finding the four parameters that actually defines H. Hypothesis class H. The aim is to find H belongs to caps H that is as similar as possible to C. Let us say the hypothesis H makes a prediction for an instance x such that hx equals to 1 if h says x as a positive example and hx equals to 0 if h says x is a negative example. In real life, we do not know Cx, so we cannot evaluate how much Hx matches Cx. What we have is a training set X, which is small subset of the set of all possible X. The empirical error is the proportional of training instances where prediction of H do not match the required value given in X. The error of hypothesis H given the training set X is as follows. This is the equation of error of H on H. Now, in this graph, we can see that this rectangle portion is C and the smaller one with the yellow color is the H containing all the positive examples. C is the actual class and H is our induced hypothesis, the point where C is equal to 1 but H is 0. The point is called false negative and the point where C is 0 but H is 1 is called false positive. Other points, namely true positives and true negatives, are correctly classified. One possibility is to find the most specific hypothesis S, that is, the tightest rectangle that includes all the positive examples and none of the negative examples, as you can see in this graph. In this figure, this is S, which is the tightest rectangle with all the positive samples. This gives us one hypothesis as H equals to S as our induced class. Note that the actual class C may be larger than S but is never smaller. Now, the most general class hypothesis G is the largest rectangle we could draw that includes all the positive examples and none of the negative examples as seen in this graph. You can see this is the border area of C and it has no negative samples here. Any H belongs to H between S and G is a valid hypothesis with no error said to be consistent with the training set, and such H make up the version space. You can see here. Given another training set S, G and the version space, the parameters and thus the learned hypothesis H can be different. We choose the hypothesis with the largest margin for the best separation. This portion is defined as the margin. The shaded instances are those that define or support the margin. Other instances can be removed without affecting H from this figure.